Hello everyone, in this tutorial we'll be going over how to simulate a high pressure blast wave propagation in OpenFOAM. We'll be using the sonic foam solver in which the air can be compressible and supersonic speeds can be simulated. So as usual, we have our case files that contains all the OpenFOAM simulation configuration files. The clean script, which you can use to restart your case by deleting all generated files. The mesh script written in Gmesh. The README, which contains basic information about how to run the case, and our run script. So our run script differs from usual, so I'll be going over that in a little more detail during this tutorial, but let's first go look at the mesh. So it's just one file. Here we have our parameters. These are sort of like the physical dimensions, and these represent the grid sizes. So you can change these values to your liking. And this wedge angle is determined by the OpenFOAM requirement on axisymmetric simulations, where the domain has to be a 3D wedge of 5 degrees. And this is where the actual geometry is drawn. So if you're not familiar with basic Gmesh syntax, please check my earlier videos on Gmesh. But these points represent the spherical source, where we'll define a spherical region where we'll initialize the pressure to be very high. So we draw a circle here, and since it's axisymmetric, it's actually a sphere. Here's the circle line, the circle arcs, as well as the line, which coincides with the line of axisymmetry. And these are the domain points that go that define the outer domain, the boundary. I'll explain it more as we visualize the mesh. And these lines just basically iterate through the points I've just created. You'll notice that I put these little markers here to denote the beginning, and since I do that, I can reference it by offset, and just with this for loop generate all the lines in sequence of the points. Yeah, and then after we make all our lines, we define the line loops here. So this is the source loop, the spherical high pressure region. This is the source surface, which uses the source loop to actually make the surface, the 2D surface, which we'll extrude later into a wedge. Same with the domain loop, domain surface, and here's where we actually rotate the surface. We actually rotate it to negative 2.5, or actually 2.5. You can see this wedge angle divided by 2. We rotate it half the wedge angle in one direction, so we can just do the extrusion, and the XY plane will just go through the center of the wedge. So that's why we rotate it, then extrude it. And so all the extruded new entities are captured in this variable domain entities, and then we finally reference the domain entities to define all the physical surfaces and the volumes. So in this is very simple. We just have the wedge and the walls, the outer boundary walls, and we need 2 physical volumes. So this is the normal. This is the most of the domain, and this blast source we name so that we can easily assign an initial condition to it. So let's take a look at it. It's a very simple domain here. So here we have our blast source. This spherical region will be where we define a uniform high pressure. And then once we start the simulation, this high pressure will of course create a wave that will go out and propagate in the domain. And we've created this arbitrary little obstacle here just to see the effects of the contact of the wave with some obstacle. And what happens in this case is it reflects the pressure wave. Yeah, so as you can see, it's a simple wedge. So physically, actually, there's like a circular fence with a spherical high pressure source in the center. So a very arbitrary setup, but a good starting point if you want to simulate blast wave propagation. Yeah, and all the boundaries are set as walls. So there's like we're like in a cylindrical room when an explosion happens in the center. Let's just take a look at the mesh, because why not? It's pretty coarse. Finest at the source, and then I get coarser, you know, around the everywhere else. Yep, that's pretty much it. So now let's go over the case configuration files, because it is a little different from what we've seen before. So one key utility, well, I guess we can just look at the run script here first. So most of these are pretty much the same. We make the mesh, we convert it to OpenFOAM format, we adjust the dictionary to fit the format, and this is how we set the initial conditions for pressure in the spherical region. We use the set fields utility, which is a built-in OpenFOAM utility. But what set fields does is it writes your initial condition as you specified in the set fields dict. We'll take a look at that later. It writes it to your boundary condition file, the in our case 0p file. So it writes the values there. So that's why we keep this p original, because when we clean the case, we don't want like all the field data for every mesh, for all the cells contained for a given run into the repository. So we just keep the original, and then we copy it over to the p, which will be overwritten by the set fields. And then finally, we run SonicFOAM. So let's take a look at the set fields dict, which you can find in case system set fields dict. And here it's just one specification. Regions to cell, set blast source, and blast source is the name we gave in our if you remember from the gmesh file, it's the name we gave the spherical region. So it knows it's ID'd by name. And for some reason OpenFOAM needs an inside point. So just specify any arbitrary point inside the region that we made. In this case it's 0.001x, and then otherwise 0y and 0z. So yeah, these are XYZ coordinates. And this is the actual value you want to set it at. So I've set it at 10 times standard atmospheric pressure, which is 1 million pascals, over 1 million pascals. Standard atmospheric pressure is 101,325. So just to give you some like a familiarity, a typical balloon is on the order of hundredths of atmospheric pressure. A typical car tire, is inflated to about 3 times atmospheric pressure. And so I'm using 10 times. So this is like 3 times as pressurized as 3 times the pressure as a typical car tire. So that's pretty much it. So you can just run the run script, and so for SonicFOAM, they don't really have like a dynamic runtime control. You have to set a fixed time step and according to like the stability and maybe accuracy, time accuracy you want. So it takes a little longer than the other tutorials we've run, but I've run it beforehand so you can see the results. So here's the pressure. As you can see, it just propagates out, and you have this like wave here, where oscillating wave, where you have a high pressure, then a low pressure, and then a high pressure region. So there's this alternating high and low pressure regions as the frontier propagates, and you could see, maybe not too clearly here, but you can kind of tell that there's some reflection here of the frontier at the wall. So this region being reflected back, the frontier is sort of combining with the low pressure region, and so you get a cancellation of the low pressure, and then it's combining here with the high pressure, resulting in an amplification of the high pressure. So yeah, let me just play that again. You can kind of see like the colors get darker or lighter as the frontier is bounced back. Yeah, so so what's interesting is the pressure actually goes below atmospheric. You can see it's 86,000 pascals. So as the frontier goes out, the center momentarily actually goes below atmospheric pressure considerably, which is really interesting. One really surprising thing was that was the extreme variation in temperature. So the temperature here is actually very, very low. It's like 100 Kelvin. That's like 200 Kelvin below room temperature, or 200 degrees Celsius below room temperature. That is quite extreme. Like, you could probably like flash freeze something, or I mean, you might be able to freeze something that was originally in the center. Yeah, the temperature drop is really pretty amazing here. That's something I kind of didn't expect. But yeah, you can see the temperature field basically follows the pressure. And we'll take a look at the velocity. So let me rescale this to the finished. Yeah, so again we have like the oscillation in high and low values of velocity magnitude that we saw with pressure. But in the case of velocity, what that means is there's like a wave of still air, or actually waves of still air propagating outward. Yeah, but yeah, this is all very interesting. I've never used this for any practical, or actually tied this to any practical application, so sorry if my comments seem a little uninspired, but yeah, I just made this simulation off the suggestion of one of my comments, and I hope this is useful as a starting point for you. But nevertheless, it was very interesting to set up. We learned how to use the set fields utility along with using Sonic Foam, which I think I only have one or two other videos using it. But yeah, that's all there is for this tutorial. If you have any questions or suggestions, please let me know in the comments, and thanks for watching.